Cool.
Okay, so now we're starting with our review session on recursion. So I'm Regina, and that's Addison. And feel free to ask any questions that come up either through voice or through chat. And as a final reminder, the slides are at this link, links.cs61a.org/recursion review if you want to look at them while we're going through the slides. So our first slide is just the basic 3 steps for recursion. The first one is the base case. And to write this, you think what is the simplest possible input you can give to your function so that you know what to return right away. The second is the recursive call, which is what makes your function a recursive function. And that's when you think, how can I take the input that I'm given and call my function on a smaller input to help me write the overall function. And finally, the third step is using the output of your recursive call to solve your overall solution, to solve your overall problem. And keep in mind that even though we put these in this order, you don't always have to start with the base case. Sometimes it is more intuitive to start with writing the recursive call.
Yep, and we're going to talk about some tips on solving recursive problems. So generally, recursive solutions will have some kind of if, elif, and else structure, where you check the base cases first, and then you check some kind of edge cases, followed by your recursive recurrence relation. So when you're writing the body of your function, you can pretend that any call to your function with a smaller input will result in the correct output. So you basically pretend that your function is already complete and perfect. And this is what we call the recursive leap of faith. Something that might help is making sure that each return statement returns the correct data type. This will make sure that your recursive calls are correct. And the last thing is, if you already have a base case, you have to make sure that each recursive call to the same function helps you get closer to the base case so that you don't end up with some kind of infinite loop. All right, that being said, let's go ahead and take a look at a very simple problem that we went over during discussion 3. So this problem is factorial, and you might remember this problem. So the way that factorial works is factorial of n is defined to be n times n minus 1 times n minus 2 all the way to 1. And we can write this as a recursive relation. So instead of writing it out like this, we can write it as something like n factorial is equal to n times n minus 1 factorial. So this is a minus. And the reason for this is because we see that, this thing right here is n minus 1 factorial, and it just factors out nicely. And this means that our recursive relation can be written like this. We can say that the factorial of n is equivalent to saying n times the factorial of n minus 1. Okay, so hopefully this was a review for you all. And this is a step into showing the 3 steps we had. So I guess that there is one particular thing that we didn't mention here, but there has to be a base case that we need to handle. So we need to handle the case if n is equal to 1, we're just going to return 1. Right, and we can go ahead and see the output on the next page. Yeah, so let me insert that. If n is equal to 1, we're going to return 1. Right, so this shows our 3 steps of the recursion. So the first thing is the base case. The smallest input to factorial here is n is equal to 1, and we handled that by just returning 1. And then assuming that we don't have the smallest case, the way that we can reduce it to a smaller case is by multiplying n by the result of a call to factorial that we assume works. Okay, so let's go ahead and move on to a more complicated example and give you guys some time to work on it. So the next example we have is list prod. List prod takes in a list, and we expect the product of all of the numbers in the list to be returned. So if the list is equal to something like 1, 2, 3, 4, then doing list prod of list should give us 24. All right, we'll give you all around 5 minutes, and then we'll go over this problem. Feel free to message us if you have any questions.
And when you're done with the question, please go to the participants tab and click yes, so we know that you're done.
I need a haircut.
Sorry, did you have a question?
All right, can we have a no if you need a little bit more time? Okay, I think people are probably good. All right, so we're just gonna go ahead and go over the solution. All right, solid. So when looking at this problem, it might be pretty tempting to write an iterative solution. So an iterative solution might look something like this. List prod of list. And we might have something like total is equal to 1. And then we might want to loop through everything in the total, multiplying it in there. For element in total, we can do something like total times equals element, and then we return total. But there's not enough spaces in this problem for us to fit an entire for loop. So we realized that we can actually condense this to a recursive solution. And the way that it works is we said that like we start with like a total that is just one element, and we realize the simplest case to the input of this function is if list only contains one element. So in the case where we had list is equal to 1, for example, then we would only have then 1 would be like the total product. But in the case where we have something like 1, 2, 3, 4, we can do something like this. We can just take the first element and then multiply that to list prod of the remainder of the elements right here. 2, 3, 4. And that's how we can rewrite this in a recursive manner. So if list, where's my eraser? If the length of list is equal to 1, which means we only have one element, then we can just go ahead and return the 0th element, meaning the only element in the list. Otherwise, we can just return the 0th element multiplied by list prod on the remainder of the elements. And that's the entire implementation. So let's go ahead and take a look at the solution. So here it is, and it's a little bit more clear to see. And feel free to ask if there are any questions about this. Okay, the next one question was, can we use dot first and dot rest? So dot first and dot rest only works for the link class. So if you had something like link and you have some kind of link is equal to link of something like that, then you can use the dot first and dot rest. And because this is just a regular Python list and it's not a linked list, we can't use dot first and dot rest. Another question is length a built-in function? So this length right here is a built-in Python function, and it returns the length of a regular Python list.
Oh, but it does say don't use any built-in functions. I think the spec is referring to built-in functions such as sum, which take in a Python list and give you some value.
Yeah, we'll edit the slides to reflect that.
And
Another
then we
question
also
was, yeah, go ahead.
Can we put if not list and return 1? So if not list is checking if the list that we're given is an empty list. However, the spec says assume that list contains at least one element. So that means that we would never hit our base case.
Yeah. Cool. All right, let's go ahead and go on to the next question.
So this question is won't you be my neighbor? And it's a past midterm question. We're going to ask you to implement repeat digits, and it takes in a positive integer n. It returns a number with each digit of n repeated. So you can see the doc test on the right. Repeat digits of 1, 2, 3, 4, and we want it to give us 1, 1, 2, 2, 3, 3, 4, 4. So I'll be writing some hints on the screen on the left side, and if you don't want to look at them, then just don't look on the screen on the left side. We'll give you about 5 minutes. And again, when you feel like you're done, please go to Participants tab and put a yes. could you put a no next, yeah, could you select no if you'd like 1 or 2 more minutes to work on this question? Okay, we'll do about 2 more minutes. Okay, let's go over the solution for this question. So we're given this number n, and we want to repeat all the digits. The skeleton code kind of gives us a hint because it names these variables for us, last and rest. And when I see those names, I kind of think like in this context, last and rest would mean like the last digit and the rest of the digits. So to get the last digit of a number n, what I would do is mod it by 10. So n mod 10 would give us the last digit of a number. And to get all the rest of the digits of the number, we just cut off the last digit. And to do that, we floor divide it by 10. So n floor divide by 10. So in the case of the dog test, last would be the number 4 and rest would be the number 1, 2, 3. And now here's a space in the next line, if something, return something. And that's going to be our base case. So can somebody put in the chat what they think the smallest possible or the simplest possible input would be for this function? Yeah, number is less than 10. And a number less than 10 means that it's just 1 digit. So all we need to do is repeat that digit and return it. So to find out if a number is less than 10, we would check the rest, because if a number is less than 10 and we mod it by 10, then the rest would just be 0. So if rest is equal to 0, then we would return that last digit twice. And to do that, I shift the last digit over by 1 by multiplying it by 10, and then I add the last digit again. So in the case of this dog test, it would be 4, which is last, times 10. So we get 40, and then you add last to it again, 4. So in the end, we return 44. Now in our last line, it's the recursive call, and we can tell because of these parentheses, which is telling us we're calling a function. So we know the recursive function, so the function we're going to be calling is repeat digits. So repeat digits. Let's just shrink that a little. And what's the input to repeat digits that can help us solve our overall problem? So we know we want to make the input n a little bit smaller to call our recursive function. And a way to do that would just be to get rid of the last number and call repeat digits on the rest of the number. And we see here that we've already instantiated a variable, rest, that has this quantity in place. So we would be calling repeat digits on rest. So if we call repeat digits on rest, we've repeated all of the rest of the number. So we would get down here 1, 1, 2, 2, 3, 3. But in the end, we want it to become 1, 1, 2, 2, 3, 3, 4, 4. So to get this final answer, we want to transform 1, 1, 2, 2, 3, 3 by shifting it over by 2 and adding our last number twice. So to shift the number over by 2, we have to multiply it by 100. 100. And the thing we have to add at the end is just our last digit twice. And that would just be the same quantity as our first return statement. So that would be last times 10 plus last. So if we go on to the next slide, so clear all the drawings. This is the overall solution. Are there any questions?
So the reason we do rest equals 0 instead of n less than 10 in the base case is because rest is what we're editing, right? And n is not what we're editing in this case because rest is taking that position instead of n. Or could we also do n is less than 10?
I believe n less than 10 could also work as a base case.
Okay,
because
cool.
it's testing the same thing.
All right, thank you.
Any other questions? Okay, so now we'll be moving. Oh yeah?
Yeah, and because in the beginning, the last line returns is very pretty long, and I didn't finish out the last part. And can you give some suggestion and how can we decide if the blank is very long and there are some breaks in the return? How can we decide that? Thank you.
How can we decide what to put inside of the last blank?
Yes, if there's, because in the previous slide and there are 3 blanks in the return
Here?
of 4, yeah. How can we decide that in the beginning?
Okay, so seeing a lot of blanks can make it very scary, but the blanks are actually kind of helping you because they're giving you clues. So the way I think about it is like, first, you see the skeleton code, and last and rest tell you what to put here. In the last return line, there are these parentheses, which is telling you you're going to be doing a recursive call, and you know like what function you're calling in your recursive call because it's a recursive function. So you would just put repeat digits in this spot, and that's already taking care of like one of the blanks for you. And the rest of the blanks are in this blank. What should you put in your recursive call? This blank is, these 2 blanks are, how can you change the output of your recursive call to give you the answer for your overall function? So sometimes it can be scary seeing a lot of blanks, but I would suggest maybe trying to understand the logic of the question first before seeing how you can shape your code to fit into the blanks. Does that make sense?
Yes, thank you.
Okay. Okay, then we'll be moving on to the next question, which is repeated.
All right, so in homework 2, you saw this function called repeated, which takes in the arguments f and n. So it's the second function on the bottom, and it returns a function that is equivalent to applying f n times to a new input. So this time we want to write repeated recursively, and you'll want to use compose 1, which is on the top and included for your convenience. And once again, click the yes button when you're ready, and click, click no if you would like more time. But we're gonna give you like another 5 or 10 minutes.
And again, if you want some more time for this question, please put a note. Okay, so one or two more minutes. Okay, so we're going to go over this question now. If we look at the skeleton code for repeated, we see it is an if-else kind of structure, and it is already telling us what the base case is. The base case is when n is equal to 0. So if you give repeated a function and 0, we don't apply f at all. So what we want repeated to return is just a function that doesn't apply anything to the input. And that would just be an identity function. And we can't really fit in a deck statement into this one line. So this is where you would use a lambda to define a function. So here on this first return statement, we would return a lambda function that takes in one argument, and it just returns that argument. And this is the identity function. Now, the recursive call is a little bit more complicated. We want to use compose one. So I'm just going to write compose one somewhere. And we know that compose one will take a function, take two functions and compose them for us. So if we're thinking about this recursively, we want to use a call to repeated somewhere, or we want to use a call to compose one somewhere. We know that compose one will kind of add two functions together for us. So if we want to utilize compose one, we would give it f first, and then the recursive call to repeated. And now we know that compose one will be giving us a function that will keep calling f on the input. And we have to figure out what is the input we're giving to our recursive call. We know that repeated takes in a function and the number of times that function is called. we don't want that function to change between calls to repeated. So the first argument is going to stay the same. It's going to be f. The second argument is going to be n minus 1. And it's n minus 1 because one of the calls to repeated is accounted for in this first argument to compose 1. And something you can do to check your code after you're done writing is to see, no matter what number I put in for n, will it eventually become the base case through all the recursive calls? And yes, because n is a number, and if you keep subtracting 1 from it, it'll eventually hit 0. And if we go to the next slide, I'll clear the drawings. You can see that this is just the answer. So there's a question. Could you explain why we return a lambda for the base case? How is that equivalent to applying f 0 times? So if we're applying a function 0 times, that means we're not changing the input at all. And if we don't want to change the input at all, if we want to just take it in and give it back out, that's just an identity function. And so that's why we write the lambda. And the reason why we use a lambda instead of defining it with a def statement is because we only have one line and we have to fit our solution on that line. And there's another question. Can you go through why compose 1 takes in repeated as its second function? Yeah, so compose 1 takes in these two arguments, f and g, and it returns a new function that kind of just wraps f around g. So if we wanted to have an original call to repeated with a function f and maybe n equals to 3, so repeated f3. It's the same thing as calling f on an argument 3 times. Like, this is what we want to happen eventually. So repeated f3 is giving us a function that we can call on x and will give us this. So it's like lambda x. This is kind of pseudocode. It's not the same thing as what we're doing in repeated, but this is what we want our eventual function to look like. Compose 1 takes in the f. So if I move this a little bit, move it up here. Compose 1 takes in the f and it kind of wraps it around the rest of the repeated functions. So if we call repeated on f and 2, this is the same thing as wrapping f around a function that will call f on an input twice. And overall, it will call f on that input 3 times. So that's why compose 1 will take in repeated. Okay. Any other questions for this problem? Okay, then we'll move on to the next one. And as a reminder, if you have any questions about past problems, you can also send them in the chat as well. So, okay. Now we're going to be doing group link.
All right, so group link tells us we have a function, or we have a function group link that takes in f, which is a function. It's a one argument function, and link instance s. So here we're using linked lists instead of regular Python lists that we were working with earlier. This function is supposed to return a linked list of groups. And I'll explain what groups are in just a little bit. We can take a look on the upper right where there's several doc test examples. So let me draw this in. We have some examples right here. And we can see that if we define 5 to be 3, 4, 5, 2, 1. So let me draw this in. 3, 4, 5, 2, 1 would look something like this. 3, 4, 5, 2, and 1. We see that passing group link with this function, x mod 2 with 5, will basically create two groups. We have this group right here, and then we have another group right here. So what is this function doing? Well, basically it's saying all of the elements that return true for this particular function are going to be put on this side, and all elements that return false are going to be put on the other side. And this function basically says, it basically returns 1 if it's an odd number. So like if you pass in 3 to this lambda, it'll return 1, or if you pass in 5, it'll return 1. But if you pass in an even number like 2 or 4 or 0, it's going to return 0, which is falsy. And so we see that group link basically takes that function and it applies it to every sequential number. So it looks at 3 and it says, well, 3 belongs in the group of 1s because it's an odd number. So it puts it on this side. And then it looks at 4 and it says, well, that's even, so it belongs on the other side. And it puts it here. And then 5 belongs on this side, 2 belongs on that side, and 1 belongs on this side. And that's really messy, so I'll clear it really quick. And so we see that we get two groups, one of odd and one of even. And you can verify that it's the same thing for the second case. Something else that I would like to go over is filter link. This is included on the study guide. And what filter link does is it's really similar to the built-in function filter that operates on regular Python lists. So the regular function filter basically takes in a function f and a list lst, and it returns all elements. It's basically doing something similar to a list comprehension, where it takes lm for lm in list if f lm. So it basically takes all of the elements from the list if the function given to filter applied on that element is truthy. So that was really long. Filter of f on a list basically takes all elements from the list if applying f to that element returns true. And what filter link does, it's the exact same thing, except instead of taking in a regular Python list, it takes in a linked list that we define. So it takes in every single element from the linked list if applying f on that element is truthy. And so we'll give you some time to think about this, and we'll come back in around 10 minutes. All right, I wrote a hint in the code part of this. And please click yes when you're ready to move on. All right, please click no if you would like a little bit more time. All right, we're going to go ahead and explain the problem. So let's take a look at what's going on in the second test case. So the first one, I said that there were all of the odd numbers, and then there were all of the even numbers. So let's see if that applies to the second case. In the second case, we see that there are actually 3 links. So there's one link here with just a link of 3. Followed by a link with, with a link that has 4 and 1, followed by a link that has 5 and 2. So what's really happening? Well, it turns out what group link is doing is it's looking at all of the possible outputs of this lambda function. So in the first case, the lambda function had 2 possible outputs. It had 0 and 1. So it's possible for a number to be 0 mod 2 and 1 mod 2. But for the second case, it's possible for a number to be 0 mod 3, 1 mod 3, and 2 mod 3. And so that's why it grouped the elements like this, or the top and the bottom, so we can understand a little bit better what's really happening here. So for the top example, we have a link. That's this link right here. And the first element is this entire thing. So it's this entire thing right here. And so we have a linked list of 3 with 5 and then 1. Okay. And the second thing is going to be, let's see here. Let me move my screen around. Second thing is going to be a linked list element with nil here. And this thing is pointing to a 4 and then a 2. Let me verify that. Yeah. So that's that diagram. And let's take a look at the bottom diagram. We have a 3 as the first element. So just a link with 3. And then the second thing is a link of 4 and then 1. And then the third thing is it's going to be a link of 5. Whoops. 5 and then 2. Like that. So we see that it's like a linked list of linked lists. The first link, or like every element within the linked list is a linked list that has the same outputs for this lambda function. So how can we implement this? Well, we see that we have 2 calls to filter link. And then we know that this function must be recursive. So a way to handle this is we can say every single time we want to grab all elements from this linked list that have the same output from this function as the current element we're looking at. All right, so let's break that down. So we know that we can call filter link, or we know that we can do s. How come I can't write? Okay, we know that we can do s dot first to get the current element inside of our linked list. And we can call filter link on, let me move this. We know that we can do filter link lambda x. X is equal to s dot first, comma s. We know that we can take this and grab all of the elements from s that are the same as s dot first. That's what our lambda function is doing right here. But what we really want to do is we want to find all of the functions where the functions of them are equal. So again, what this allows us to do is it allows us to compare, it allows us to take all of the elements from this linked list where the function of that element is the same as the function of the current element we're looking at. And so we can stick this straight into A. So this will just go straight into A. And this gives us all of the elements for our current box. And for all of the elements of the remainders, we want to grab all of the elements that are remaining. So all of the elements that don't equal our current s dot first. And so the way we can do that is we can just do filter link of lambda x. F of x is not equal to f of s dot first. And we're going to put that right here. And this basically allows us to take all of the elements out that are not equal. All of the elements out whose functions are not equal to the current element function. And so this gives us two linked lists. And remember that our output is supposed to contain a linked list of linked lists, where each single linked list is one output that has all of them outputs of f equal. That was a little bit confusing. So we basically want to return a linked list and stick A in, because that's our first group where we know all of the elements are equal. And we want to call group link on the remaining elements of S, basically all of the elements whose outputs we're still unsure of. And so we're going to call all of them on B. And that completes the function. So again, I'm going to recap this because it was a lot. The first thing we did was we pulled out all of the elements whose function's output was the same as the function output of s dot first. And we stick all of those into one linked list, which is called A. And the second thing we did was we pulled out all of the elements that were remaining. And those are basically the elements whose function's outputs are different than the function's output of s dot first. And we saved that as B. And we realized that if we call a group link of f on B, that gives us the remaining linked list. And we can stick those outputs inside a new linked list of link A, comma group link FB, and that gives us our output as needed. Cool. So are there any questions about this problem?
Just out of curiosity, what would you guys say would be like a good general strategy for recursion? Would it be to analyze the doc tests, identify a base case, and then identify the recursive case? Or is there something a little bit more detailed than that we should look for?
Yeah, so I think understanding the doc test is always a good place to start. So for this problem especially, understanding why the function gave us this output gives us a really good starting point of saying, how can we break this problem down into something we can handle in this particular recursive call versus in the future recursive calls? So I think starting from the doc test is a good place to start. Maybe Regina has something to add.
It kind of depends on what question you have. And sometimes they give you hints as to the base case or the recursive call. But I would also suggest, like, if you have one of them, if you have either the base case or the recursive call, they are like intrinsically linked because the recursive call will eventually take you to the base case. So you can try to deduce one from the other.
Okay, cool.
Yeah.
Thank you. And then
Yeah.
also, does the order matter in our recursive call at the bottom where we're doing link A, group link F, B? Or does it not matter, like where A goes before B or B goes before A? Does that not matter?
So you're saying, like, can we swap these two?
Can we swap the A and can we swap A and B? Not like A and group link, just A and B, the variables themselves.
So like this one and this one.
Yeah.
These two. Okay. So we actually cannot do that. And the reason for that is because the reason that we can store A as the first element inside our linked list is because A contains all of the element for which this function produces the same output, right? And if we put B in there, we know that the elements in B don't necessarily produce the same output, if that makes sense. So we would have to like recurse later to put those elements inside the right groups. And so that's why we have to call group link on the elements inside B as opposed to elements inside A. Does that make sense?
Yeah. So because A is true, it has to be where it is. And because B is the false values, it has to be where it is.
Yeah. So let's go ahead and go on to the next slide so we can see that a little bit more clearly. Yeah. So we see that if we tried to put B here, then like, for example, this doc test wouldn't give us the right answer. It would stick 4152 inside the first link and then 3 inside the second one.
Something else to note is earlier you mentioned true and false. but the functions that we're applying don't only have a true and a false answer. So the first doc test, lambda x mod 2, has an answer either 0 or 1 for every number, because every number is either even or odd. So in that case, it wouldn't matter the order of A and B, because B is also a group where every element has the same value when F is applied to it. But in the second doc test, lambda x mod 3, there are 3 possible answers, 0, 1, and 2. And so if you switch the order, the B would have all of the elements with either like maybe 1 and 2, and A would have all the elements that have the same answer, maybe 0. And so you can't switch it in that case.
Okay, so it depends on case by case.
Yes, but the way that we've written it, A will always contain elements that all have the same answer. So we always want to have A first in the linked list.
Okay, cool. Okay, thank you.
Mhm.
Are there any other questions? All right, cool. Let's go ahead and move on to the next question.
I was muted. This question is summer camp, and it's also kind of tough. So we want to write the function sum. It takes in 2 positive integers, n and k, and it returns a list of lists containing all the ways that k positive integers can sum to n. And so what that means is if we look at the doc test, sums to 2, we're trying to create a list of lists with each having 2 elements that can sum to 2. So the only possible one is having 1 plus 1 is equal to 2. Sums to 3 is nothing because you can't have 3 positive integers adding up to 2. Sums 4 2 has 3 possible ways to add 2 positive integers to create 4. So we'll give some time for this, but we might come together a little earlier than necessary because we're running a little short on time. Okay, I know that wasn't enough time, but I want to start going over the solution now so we're able to get through it before the session ends. So when we first think about sums, just intuitively, let's try to make sense of how we can do this recursively. So the first doc test, sums 2 and 2, you know that at some point you're going to be using a number to create your sum. So you want to use a number that's positive to create your sum. And the first positive number that you can use is 1. So sums 2, 2 will use a 1, and then it will try to make a list of lists that create the rest of the n. So what I mean by that is if we originally have sums 2, 2, and if we say we want to, I can't draw an arrow with this, but if we want to use a 1, then we would be calling sums. We've already used the 1, so we want to subtract that 1 from the number we're creating. And then we can only use one more number. So because we've used one number, so this would be the recursive call that we have after we use a 1. So like count partitions, when you use a number, you have to decrease the total that you're trying to create and to decrease the amount of numbers that you can use. So this is just sum 1, 1. And what sums 1, 1 is going to give us, if we take the recursive leap of faith, is just a nested list with a 1 element 1 inside. So if we have a nested list with 1 element 1 inside, to reflect that we create a sum 2, 2, we would reflect that we used the 1 earlier, and this would become two elements inside of our nested list, 1 and that 1 from before. And so this is just a solution for sums 2, 2. So I've kind of walked through one step of using a number to create the overall solution. So we know that we're going to want to use numbers that are positive to create our sums, but we don't know like which numbers that we're using. So we could use any number that's a positive integer and also less than the number n as our number that we're using here. So to reflect that we can use all of these numbers, we have to go through all of these numbers and try this recursive call on all of them. So that's the reason why we're going through a for loop here. For x in, we're going to be going through each number from 1 to the number n, or from 1 to the number n minus 1, because we don't want to go the entire way. So it would be for x in range 1, n. And this will go from 1 to n minus 1. So x is the number that we're using. So this is like using x. If we look at the skeleton code, y is the nested list that we're returning at the end. So at every step in this for loop, we want to extend y by the output we get from our recursive call, right? With that number we used added to each element. So the output we get from our recursive call you see lives here. Oh, there's something in this chat. Oh, so someone asked, how do you know you start at 1? You can't start at 0 because you cannot use a 0 because it returns a list of lists containing all the ways that a positive integers can be used in our sums. So you have to start at 1. You cannot do range 1 n minus 1 because range is exclusive of the last number. So it will go from 1 to n minus 1 if you put n at the end. Okay. So now we look at our recursive call, sums. Here we had a number x that we said we were using. So I just plugged it in. But here, the number x may change from iteration to iteration. So that first element in sums is not going to be n minus 1, but it will be n minus x because we're using x. And then because we're only using one element in each iteration, k is not k, but k minus 1 because we've already taken the spot of one of the numbers we're using. So sums n minus x, k minus 1 is the same thing as this sums 1, 1 here. And now we get the solution from our from our recursive call. And now all we have to do to the solution from our recursive call is add that number that we used originally to the beginning of every list inside of it. So here it shows us a list comprehension. We're going through each element in the result of the recursive call. And now we just have to add this number x. We have to add this number x to the beginning of each of these elements. So to do that, it would be s plus x. Oh, what happened to the recursive call? Anyway, I'll write it again. N minus x, k minus 1. Okay. And now we're going, and we think, what is the base case supposed to be? We've finished our recursive call, and we know that at every step, we're subtracting from n and we're subtracting from k. So k would keep subtracting until it becomes maybe 1 or 0. So if k is 0, then this question is trivial. But if k is 1, then we know what to return. So if k is 1, then we want to create a nested list of lists that will give us one number that, when added, becomes that n. So you can't add a number if you only have one number. So you would just return that nested list, and inside would just be n. Okay, so somebody asked, what about the base case where n is less than k? So n being less than k, you can make that into a base case, but that case is also caught by this function. So what I mean by that is if n is less than k, for example, the second doc test, we would bypass this base case. We would go in here and we would go for each element in range 1 to n. So that would be 1. We would extend, and then we would call our sums. And at some point in our recursive calls, n would be some number, maybe 0, and k would be 1. And so you would just return, so in the case, sorry, I'll restate this. In the case where n is less than k, we're going to be taking care of that because n will be subtracted at every step by at least 1. So n will at some point reach 0 at the same time k reaches 0 or before k reaches 0. And so here, for x in range 1n, we will never go into this loop because range 1n won't occur. So we would just return an empty list y. Does that answer your question? Okay, if you have other questions, feel free to message privately or stay behind. But right now we're after time. So the review session is over, but we'll stay for questions.
As a quick question to go over for this current code, how were you able to go throughout the process of solving this question? And also, what exam is this from?
I believe this question is from summer 2015, but I'll search it up and add it to the slides after the review session.
Okay, cool. And then how did you go through the process of solving this problem? Can we go over that again? Just like what like step by step we were able to do and like generalize that?
Like this is similar to the question before that you had. It's kind of hard to say like a formula for solving recursive problems. But for this question, something I realized is that you have to have a for loop here, and you need to figure out like what you're doing inside of this for loop. And then you realize like at every point where you use a number, it has to be a number from like 1 to n. And there's no like set there's no set order in which you would use these numbers. So at every instance of calling sums, you would have to go through the entire loop. So that's why you would fill this in. And then you realize like every time you use a number, you're going to have to extend your recursive call, the solution from your recursive call. And then so that's how I figured out what to put inside of this line, y.extend. So Addison, do you have any like tips for, I guess, solving recursion in general?
I think you covered most of it. I think for this problem, it's pretty enlightening to draw out like this case right here. And in particular, I think for this problem, like drawing it out in terms of like possible paths you can take, I guess, yeah, like possible paths you can take might explain it a little bit better. So like for 4-2, you can either, if you were to do it like just by using like math, you can either take 1 or you can take 2 or you can take 3. And then you realize that that's kind of a general pattern you do. And then you realize that this X must be like some kind of range. And then you can kind of go from there to figure out what you need to extend. So basically what Regina said, yeah.
Okay, cool. Thank you guys so much.
Mm-hmm.
Question?
My question, and because the return a list, I'm kind of confused about the base case and return bracket n. Can you explain more about that?
Yeah, so if you were given sum 3, for example, sum 3, 1, the question spec is telling us to return a list of lists of the ways that one positive integer can sum to n. So the only way one positive integer can sum to 3 is if we just have a list of lists that has 3 inside. So that's what we're doing in the base case.
Okay. And also, and you both talk about the range just now because you say, and the we should from 1 to 2 to 3. We talk about that, but in the beginning, the range I didn't think about. We can use the range.
I'm sorry. Can you repeat your question?
I mean, and in the beginning, the range I didn't think about. Can use the range, and how can I decide and what part should I use? Yeah, for example, in here, use the range 1, n, but in the beginning, I didn't think about in this way. How can I decide the code? Can you give us some suggestion?
Oh, so are you saying in the case that you forget that you can use range, how you would get that list?
Yes.
Oh, so range is a function that we do teach in CS61A, so it's good to remember it, and it should also be on the past study guides and stuff. If you don't remember how to use it, Addison, can you think of another way to code it without range?
I know how to use the range, but in the beginning, I didn't think about I can use that.
Or like, is your question more like, how did we come to the realization that range was needed?
Yes.
Oh,
Yeah.
okay. Because at every point, you're going to be using a number to add to be like part of a sum that sums up to n. The numbers that you use, it only says it has to be positive. So it can be 1, 2, all the way up to n. And so for each sum, you have to make sure that you're checking all the possibilities. So if the first element, if the first number you use is 1, if the first number you use is 2, if those will create possible sums. So that's why you have to go through each number, and you get that by calling range, and then that's how you get x as each positive number that's less than n.
Oh, that makes sense. Thank you.
There is a question. Oh, Catherine Sway asks, how does it become 3, 1, 2, 2, 1, 3? I think that's referring to the last doc test. So 3, 1, 2, 2, and 1, 3 are the solutions to this recursive function. If we were to trace out all of the recursive calls that we go through when we call sums for 2, so sums for 2, it will call inside of the loop. It will call sums 3, 1. It'll call sums 2, 1, and sums 1, 1. And in that first line here, it's when x is equal to 1. Here's when x equals to 2, and here's when x equals to 3. And so sums 3, 1, if we take the recursive leap of faith, will just give us 3. Sums 2, 1 will just give us 2. And sums 1, 1 will just give us 1. And that's from our base case. So here's when x equals to 1, x equals to 2, x equals to 3. And then now after we get these answers from the recursive calls, then we have to add these x's like here. We're combining what we get from the recursive call with the x that we had before. So we're adding a 1 to this list. So we end up getting a 3, 1. Here we're getting a 2, 2. And here we're getting a 1, 3, because we've had these and we're adding the x's. And then in every step, we're extending this y with these lists. So at first, y is an empty list. we keep extending y with these lists. So in the end, y becomes a nested list, 3, 1, 2, 2, and 1, 3. And that's how we get this overall solution for sums 4, 2.
All right, I'm going to go ahead and stop the recording, but feel free to keep asking questions.